Hello everyone, welcome to Scaling Equations. This is the fourth video in the scale factor stoichiometry series. I hope you've seen the other three. If you haven't, you can certainly stop watching this one and go watch the other three. And if you have, let's go ahead and get going. In order to understand what I'm doing in this video, you need to already be able to give examples of mole balanced and mass balanced equations. You should be able to convert a mole balanced equation into a mass balanced equation. And you should already know about creating scale factors for mole balanced equations. After this lesson, you should be able to use situation and standard amounts to create scale factors for mass balance equations, and then you should be able to use that scale factor to rescale the equation, which is to say, make either more or less than what the standard amount makes. Just a reminder about scale factors now. The scale factor is the situation quantity over the standard quantity, and that's going to give you a ratio, a proportion that you can scale the entire reaction by simply multiplying it all by the scale factor. These problems will have a three-step process. Number one, you need to determine the situation and standard quantities. Number two, calculate the scale factor. And then finally, apply the scale factor to the standard equation, and then you will have successfully rescaled the equation. Let's go ahead and get to work on scaling some ammonia synthesis here. So we're going to rescale ammonia synthesis for a situation value of 2.5 grams. Here is your mole balanced equation handed to you for free. And here is the standard mass balanced equation. That how we get the mass balanced equation from the mole balanced equation was explained in the previous video. So if you need to go back and refresh yourself on that, go ahead and take a moment and do that. But let's go ahead and see what we need to do here. We need to create a scale factor. And the situation value, we've just been told pretty much straight up that it's 2.5 grams of hydrogen. And then standard values come from your equation. So there's the standard value of hydrogen, those 6 grams right there. Scale factor is, see if you can say it before I do, situation over standard. So we have the situation value of 2.5 grams of hydrogen divided by the 6 grams of hydrogen to create a scale factor of 0.4167. If you like fractions, that fraction is 5/12. So if you were making a recipe that made 2 dozen cookies, and you ran it with this scale factor, you would make 10 cookies. All right, so the grams of hydrogen on top cancel with grams of hydrogen on bottom, and we have a 0.4167 scale factor, a 5/12 batch, if you will, and it's time to apply that scale factor to the equation. So there's our standard mass balance equation, and we're just going to take the scale factor of 0.4167 and distribute it through each of the masses of the reactants and product in the standard mass balance equation. So when we multiply it by the mass of nitrogen, we get 11.7 grams. By the mass of hydrogen, it becomes 2.5 grams. And that's what needs to happen because the whole point of this was to scale it to 2.5 grams of hydrogen. And finally, multiplying it by the ammonia gives us 14.2 grams of ammonia. And now we have our rescaled equation. 11.7 grams of nitrogen plus 2.5 grams of hydrogen makes 14.2 grams of ammonia. And if you add 11.7 to 2.5, you get 14.2. So the law of conservation of mass holds no matter what scale you run the reaction at. Let's go ahead and do another example. What if we're going to scale the reduction of silver nitrate by copper to a situation mass of 2.00 grams of silver? Well, let's go ahead and look at the mole balanced equation. There it is. Convert that to a mass balanced equation. Again, I'm not showing you the work for this in this video. It was explained how this was done in the previous video. The situation value, we've been told straight up in the beginning that it's 2 grams. From the standard mass balance equation, we can see the standard amount is 215.8 grams. So the scale factor is situation over standard. So there we have the situation 2 grams divided by the standard 215.8 grams. Grams of silver cancel, and our scale factor is 0.009268. No way to make a nice pretty fraction out of this one. So let's just go on and apply it to our equation. We're going to distribute that through. And instead of taking the time to show you each multiplication, if you just distribute the scale factor through, these are your rescaled mass balanced equation. So there you go. If you are reducing silver nitrate by using copper, and the situation calls for 2 grams of silver, you'll want to use 0.589 grams of copper, 3.15 grams of silver nitrate, and you'll make 1.74 grams of copper nitrate along the way. All right, it's time for you to give it a go. here are 3 reactions for you to try: water decomposition, sodium azide decomposition, and reduction of silver by zinc. If you've watched our previous video, you may recognize these examples from that last video. And truth be told, the reason why I keep using these examples over and over is because it allows me to use the copy and paste feature. So go ahead and give it a go. Pause this video, and I will be here after you've had the time that you need to try to rescale these equations. Okay, welcome back, and here are the answers that if you rescale properly, you can see those are the new values for each of those 3 reactions. I hope you are successful at being able to rescale these equations and that you're ready to go on to the next step, which is the actual type of stoichiometry questions that you get asked in your textbook. So thanks for watching the video. I hope this was helpful, and I look forward to seeing you again soon in our next video.